So hi, I'm Pavan, and I just defended my PhD thesis a couple of weeks ago, so I'm not a PhD student anymore. But yeah, so my next step is I'm going to the University of Toronto as a CETA fellow, so I would love to talk to anyone who also is going to be there. And yeah, so with that, I just start my talk. So I'm just going to change gears a little bit and going to talk about disruptions by stellar mass black holes, not supermassive or intermediate mass black holes. And before we actually dive into these micro tidal disruption events, I just want to give an overview of the complicated lives of stars, because that's where my interest lies in. I primarily work with the interaction of stellar evolution and dynamics, and this is where tidal disruption comes into play as well. So if you look at stars, you can have single stars in the field which go about their merry way doing their stellar evolution thing. You could have binary stars which interact with each other in different ways. You can have multiple stars. We can have multiple stars with triples and quadruple stars which are bound together. And this is also one of my expertises. I primarily used to work on, not used to, still work on these kind of systems. And this is what our group at the Max Planck Institute in Garching also concentrates on, binary stars and all these interactions with each other. You can also look at the environment which stars are in. You can have isolated field stars like the sun, or you can have stars in dense clusters where stellar densities can be orders of magnitude greater than the stellar solar density. And with different combinations of these, you can have different kind of interactions. So with binary stars, you can have mass transfer and tides and so on, and these give rise to very interesting phenomena, including gravitational waves and kilonovae and thermonuclear supernovae and so on. Then with multiple stars, you have all this binary evolution stuff which happens, and you have additional orbital perturbations which can kind of enhance these phenomena. And you have interesting things like orbital dynamics playing a role as well. And then what we concentrate on this talk is single stars in dense clusters. So you can have stellar encounters, single encounters which can lead to collisions and these tidal disruptions and so on. And you can have everything everywhere as well. So moving on to dense clusters, as I mentioned before, the densities in the cores of these clusters can be high enough for these single encounters to occur, which lead to, does this work like this? Okay. Yeah, which lead to long-term dynamics changes in the cluster itself and very interesting phenomena which include the destruction and formation of binaries within clusters, and all this affects how clusters evolve in the long term. And here we come to microtidal disruption events. I don't need to give an overview of this because we've seen every talk which talks about how these work, but to provide a more cartoonified illustration of it, so I want to concentrate on the post-disruption remnant which is there. So after the star is disrupted and the tidal streams go around the black hole and everything, the star itself has lost some mass, it has gained some spin, and it has changed from its original trajectory. And all of this depend on various factors, including the mass of the star, the mass of the black hole, and how close it approaches and so on. And this is kind of what I look at in this current work. And what are the implications of such encounters in microtidal disruption events, and how frequent are these? So regarding frequencies, they're not as frequent as supermassive tidal disruption events. They're approximately 1% of that with crude rate estimates. But then these have implications such as they can help in the formation of low mass X-ray binaries, which have been traditionally difficult to explain through binary stellar evolution alone. we can talk about this later on. These also result in the growth of black holes, growth of stellar mass black holes in particular, in globular clusters, and can result in reaching black hole masses close to the intermediate black hole range as well. And observation-wise, we haven't really observed definite candidates of microtidal disruption events, but there have been some proposed transients which could have been from microtidal disruption events, including ultra-long gamma ray bursts and fast blue optical transients. Yeah, so with this, I just go with my outline of my talk. So the aims, I perform hydrodynamic simulations of these micro TDEs using a hydrodynamics code called AREPO. And my main aim is to look at post-disruption parameters, the masses, the spins, the orbits, which I mentioned before. And the reason I want to look at this is to have accurate fitting formulae or accurate results of how such encounters would happen in globular clusters. And these can be incorporated into globular cluster n-body codes for better treatment of such things. Yeah. So yeah, we look at the parameters. So we have star mass. I do not have a very wide parameter space of masses. I only look at 0.5 and 1 solar mass stars. I look at 3 different stellar ages. This is similar to the one from 2 talks before by Mega. I look at 0 age, middle age, and terminal age main sequence stars, ZAMS, MAMS, and TAMS. And black hole masses, I look at the stellar mass black hole range of 10 to 40 solar masses. And of course, the impact parameter, which I characterized by this symbol B, which is the inverse of beta for people who work on theory. It is defined as the periapsis radius divided by the tidal radius, defined as follows. There are also other parameters which could have been varied, including the orbital eccentricity, initial rotation of star, and such, so on. But with this, we just go on with simplistic single body encounters in an initially zero energy orbit or a parabolic orbit, and the star is initially non-rotating. To introduce AREPO, people who are familiar with hydrodynamics might be aware of 2 major schemes followed. One is the finite volume or static grid method. A lot of mesh codes follow this, where you have an Eulerian mesh which doesn't move really, and each have their own state variables and everything, and fluxes and volumes and everything is calculated between the cell interfaces. Then we have smooth particle hydrodynamics, where we have particles moving around, and this is a more Lagrangian approach. And you have these particles interact with each other through some smoothing kernel. What our code does, our AREPO does, is kind of a combination between these two. So you have grids. You have grids like this, which are movable. This is a moving mesh, but you still have the advantages of grid codes where you calculate fluxes between cell interfaces and so on. So shocks are treated better, for example, than SPH codes. Yeah, with that, we just look at our stellar models. We generate our stellar models using MESA, which is a stellar evolution code, and look at these 2 plots for temperature and density with respect to radius. So the dashed lines here, which are kind of hidden, are the profiles from MESA, and the solid lines are the profiles which have been converted to 3D AREPO profiles. So you can see that there is some kind of disagreement near the surface, but the rest of the star is pretty well described by just conversion from 1D to 3D profiles in a self-consistent way. And that was for a 1 solar mass star. We also have similar profiles for a 0.5 solar mass star. And we look at only the 0 age main sequence star for 0.5 solar mass stars because more evolved stars don't really exist in the current age of the universe. So here are some nice movies of the effect of impact parameter. So I would like you to look at B as a scaled version of how close the star approaches. So lesser value of B means a closer approach. So this star is almost completely destroyed within the first approach, whereas a star which approaches much farther away is left behind and it goes on. It's a partial tidal disruption, or a PTDE. Another factor which influences how much a star loses mass, how much mass is lost from a star, is the so-called density concentration parameter. This is a crude estimation of how much density is concentrated in the center of the star. So you can define it as this core density to the average density of the star with some power to the 1/3. So stars which are more densely concentrated are harder to fully disrupt. So they would have a higher, they would need a closer disruption for closer approach for full disruption. And if you see this parameter, the inverse of this parameter for a 1 solar mass star with respect to age, you see that 0 age main sequence star have low rho conc. This is the inverse again, sorry. So these are easier to disrupt, whereas the terminal age mean sequence stars which have high rho concentration are harder to disrupt. And we see the same in these simulations. So a 0 age main sequence star and a terminal age main sequence star which are approaching at similar distance of approaches. Here a 0 age main sequence star is completely disrupted, whereas a terminal age main sequence star survives and then comes back for a second disruption. And this is in the middle. So we perform a huge suite of simulations and calculate these parameters, which I present now. So the results I present now have, the parameters which I present have been calculated a few dynamical timescales after the disruption. So I look at where these parameters kind of plateau and then I use these parameters. So they might change through larger timescales, like thermal timescales. For example, the spin could decrease through time. But let's look at mass first. So I present on the x-axis the impact parameter, the closest distance of approach, and on the y-axis fractional mass loss, so more mass loss on the top. Here you can just look at the left plot for now. And this is a disruption of a 1 solar mass star with due to a 10 solar mass black hole. And this dotted dashed line here represents a star which is fully disrupted. So as you might expect, as impact parameter increases, the amount of mass loss decreases, which is kind of evident. But this mass loss is kind of follows a roughly exponential trend. This is a log scale. And similarly for a 0.5 solar mass star. These are for 3 ages of a 1 solar mass star. A 0 age mean sequence star, as mentioned before, loses more mass, which is why this is higher. And I'll just switch between this slide and the next. So the only difference between this slide and the next is that this is disruption due to a 10 solar mass black hole, and the next one is due to a 40 solar mass black hole. There is a few slight differences, of course, because of different simulation mechanisms and everything. But in general, ignoring the fitted lines, of course, you can see that approximately similar amounts of masses are lost with respect to the scaled impact parameter. So you can imagine that with just the impact parameter and the density structure of a star, the mass loss is kind of independent of the mass of the black hole itself, at least in this range of black hole mass parameters. And similarly, we see the same thing with the spin of the star as well. So here, instead of mass, I plot the spin angular momentum in CGS units on the y-axis, more spin angular momentum and less spin angular momentum, respectively, on the top and bottom. So again, when it is expected that for large impact parameters, as you increase the distance of approach, the spin up of the remnant is not as high because it receives less torque from the black hole itself. But as you bring the star much closer to the black hole, a lot of mass is lost, but it also spins up. So there's kind of like a thing where it dips off because of mass loss. But the main thing to notice is that near this, so close to the tidal radius, 1 represents the tidal radius, classical tidal radius. You can see that the remnants could approach very close to these dashed lines, which represent the approximate breakup angular momentum of the stars. So they're rotating quite fast, even when they're initially not rotating. And this is similar with 0.5 solar mass star, and the same thing with a 40 solar mass black hole instead of a 10 solar mass black hole. I'm sorry if the fitted lines were kind of distracting, but yeah. And finally, we look at the orbits of the parameter, and this is kind of defined by how much asymmetric mass loss happens from the remnant. This was also mentioned a bit by Debjyoti in the previous talk, but I can explain it a bit further. So when you have the two tidal streams, depending on how much asymmetric mass loss happens, the remnant can get a kick. If there's more asymmetry, the kick would be higher. So if the black hole mass is not very high, and it is if the star is also quite densely concentrated, it would receive a very small kick, and this would result in the star being bound to the black hole. So it would come back again for a second disruption. So you would see it completely destroyed in the end due to multiple passages. But if the mass asymmetry is quite high, even this tidal stream asymmetry is quite high, and then the kick is large, and the orbit and the remnant can get kicked out of the system on a hyperbolic orbit, and the velocity at infinity could also be quite high, in the order of hundreds of kilometers per second. So they would pretty much escape the cluster as well. And here I show a plot of orbital eccentricity. So the dashed line represents a parabolic orbit or a zero energy orbit. Anything above is hyperbolic, anything below is eccentric. So starting from an initially parabolic orbit, we see that in the case of 1 solar mass stars and 10 solar mass black holes, all the orbits are bound, but it's not a monotonic behavior. You have some kind of upturn here, and this is due to asymmetric mass loss. It gets kicked in a particular direction. In the case of a 0.5 solar mass star, the mass asymmetry is much higher because it's a lower mass star. And you see that this happens enough that this remnant is kicked out of the system completely, so it becomes unbound. And this situation is more drastic when you have a 40 solar mass black hole. While in the previous case, you saw that the 1 solar mass stars were all bound. In this case, 1 solar mass stars can also be unbound. For example, in the ZAMS model here, zero age main sequence. Yeah, and I would just like to briefly mention other effects which the remnant might have. So we saw in Mega's talk from before, the remnant is more puffed up after disruption due to tidal heating and so on. So something which looks like this initially might look like this. If you notice, the cells here are irregular. This is how Arepo cells look like, the moving mesh cells. But the previous couple of talks, the Mega's talk also went further and evolved the remnant using cellular evolution code. We don't do that here in my study, but then we have from other studies like Ru et al., where they have done this. They have evolved the remnant using MESA, and a star which was initially, this is the HR diagram, by the way. If you have a star initially here, it could go a bit to the top left of the diagram after disruption. So it becomes hotter and more luminous as well, at least for some thermal timescales. And finally, I would just like to briefly mention that there are also like nice things which can happen in globular clusters, where instead of a single encounter, you can have a single binary encounter. And here you have a binary star system which approaches a black hole. Here you have a star which approaches the binary black hole system. And then depending on the phase parameters, the inclination angles and so on, a lot of interesting events can happen. And this is quite well detailed in these 4 papers by Tae-Ho Ryu, considering all different combinations of encounters of such systems. So do look into that if you're interested about this. Yeah. With that, I'd just like to summarize my talk. So yeah, we have these parameters which we looked at. We performed a suite of simulations, and yeah, the other things were just describing the parameters. So the mass loss decreases when you have farther distances of approach. The spin also increases when a star comes closer to the black hole, and the orbital evolution is quite specific, and it doesn't follow a really monotonic behavior. You need to look at the specific case and calculate the energies to figure out how exactly the orbit looks like after disruption. And these parameters are fitted in my, we have provided best fit formulas for these parameters, and these can be used in globular cluster simulations. And yeah, that is pretty much my talk. Thank you.
Questions? Go ahead.
I'm sorry. Thank you for the very clear talk. Could you make me understand the fate of a star, whether its center of mass remains bound or unbound, looking at the energetic budget?
Yeah, okay.
So the total energy is kinetic plus the binding energy.
The binding energy itself, and you look at the tidal energy, and then you also look at the self-binding energy of the star, and then you also have a kick which can be calculated. So these three components, and depending on whether it's positive or negative, you can figure out whether the center of mass will be bound or unbound.
Can you give me an example?
An example of what?
You showed that, for instance, starting from, where was it?
Like this?
No, the previous one from hyperbolic, how was it? Starting from parabolic, then
Yes.
you end up being bound.
Yeah.
Where does the energy goes?
So in this, the energy goes into this asymmetric kick loss, which has a dependence on the mass of the ratio of the mass of the black hole to the mass of the star. In this case.
Okay, so
I don't have
you can discuss.
Yeah, sure. I have the exact formula as well. I can talk about it.
Yeah, very interesting talk. Thanks. So I was just wondering. I mean, the amount of energy you're going to get out is going to be something like 10 to the 39 or so, I think, isn't it? For that size of a black hole. Mm-hmm. Which means you're only going to be able to see it in relatively nearby galaxies. So
okay.
What do you think the rate is per galaxy? I mean, it must be really difficult, but
I honestly don't know the observational rates. I only know like per galaxy. Okay, per galaxy rates. Okay, they're approximately 10 to the minus 4 to 10 to the minus 5 per year per Milky Way-like galaxy. So considering approximately 100-ish globular clusters and the average density of clusters in the Milky Way galaxy. So, and 10 to the minus 4, 10 to the minus 5 might be optimistic as well.
Oh, really?
So it can be a couple of order of magnitudes on the other side as well.
Okay, great.
But I hope you observers can observe these things.
Thank you for the interesting talk. So you mentioned in the case of partial disruption events, sometimes you spin up the remnant. Mm-hmm. I am wondering if you have some cases where you can maintain the spin of the star, especially since the remnant pops up. I'm wondering how the angular momentum transfer would change the spin of this remnant later through stellar evolution, but just curious, just for the hydro simulations,
yes.
Do you have any cases you can maintain the spin?
I mean, if you say maintain the spin, the closest approach of distance should be much higher than the tidal radius. For example, with the impact parameter of twice the tidal radius, you would have a lesser spin up compared to a closer distance of approach. So you could expect this to decrease further.
But this is not a time evolution, so like...
Okay, you mean through time.
Yes.
So the star itself might spin down, is what you're saying.
Do you have any cases you can maintain the spin high?
I don't know. I don't think so. I don't know.
Okay, thank you.
Yeah, great talk, great movies. So I also have a question about the rate. So I want to understand it a little better. So for every like star in a globular cluster, or like one in how many would have these kind of peculiar, like brighter than usual, like nitrogen enriched, those kind of peculiar characteristics?
Are you asking me?
Yeah, one in how many stars in like a Milky Way globular cluster would have this kind of peculiar signature?
Okay, that that I don't know. I don't know really.
Yeah, I think you already mentioned the numbers so that we can talk later. Yeah.
Yeah, I wouldn't know about the nitrogen enhancement much though.
Hi, very nice talk. I have a question similar to a previous one, but I just want to clarify something. I think the asymmetric mass loss that you were mentioning as a mechanism to give a kick, in the case of supermassive black hole, it was proposed before as giving a positive kick. But I understand that in your case, you're getting a negative kick.
No, I mean.
Oh no. Okay.
You mean in the bound cases?
So you start from a parabolic star, right?
I start from a parabolic star. Yes. So, yeah, the ones where it gets unbound, they are positive kicks.
Yes.
I don't know if I would call the bound cases negative kicks. It's just the self energy of the star reduces.
But that's also because of the asymmetric mass loss.
In the cases where they're bound, it's not as asymmetric as in the case where there's a positive kick. If it's asymmetric, they would lead to a positive kick. More.
So I guess it's the same question as Elena's, but what is it that makes it bound then?
What is it that makes it?
It's not asymmetric mass loss. You don't have to answer now. We can talk about it.
It's just dissipation of the orbital energy and injecting it into the envelope of the star. So
okay.
It's like a tidal capture scenario.
Okay, okay.
Oh, yeah.
Yeah.
Into the envelope of the star. So you're removing energy from the orbit. Yes. It's just a balance between. But both happen, right?
Yeah.
Both. You could have both scenarios based on the impact parameter. We can all chat later, maybe.
Yeah. Yeah.
Thanks, very nice talk. I wanted to ask just two curiosities about if you did you explore different metallicity?
No, I only looked at solar metallicity stars, but metallicity would just change, at least because these things happen in a dynamical time scale, they would just change how compact the star is, how centrally concentrated the star is.
Okay.
So it wouldn't affect it in a chemical way, if that's what you mean.
Okay, I see. And the other is about the time scale of this event.
Yeah, so depending on the distance of approach, it would be like a few hours.
Okay.
The scale of few dynamical time scales of a star.
Okay. And very last one, about the fitting formula. Did you plan to provide this fitting formula also for a case of multiple system, for example, binary black hole that destroy stars?
Those would be hard. Those would be
cool.
They would be very hard because even a small change in phase would change how the star approaches the black hole. So I would assume that formula is chaotic.
Yeah,
There's no formula.
I know. Yeah, okay. Thanks so much.
Hello. Nice talk. I have a question related to the previous question about the remaining angular momentum in a star. So is that angular momentum mostly from just the tidal spin up, or from some external angular momentum transport from whatever particle that is eventually lost?
Okay. Like you mean the streams which are lost?
So you have a star passing the black hole and loses some mass, and then the remaining star has some angular momentum. I'm asking, is that angular momentum from the by themselves
tidal spin-up
or
mostly.
from the particle that was lost?
Yeah, it's tidal spin-up.
Okay, so there's no, so basically that means the angular momentum transfer mechanism is not going to be very important in this scenario, because if you're only considering the total angular momentum of your randoms. Okay.
Yeah, exactly. Yeah.
Thanks.
All right, any more questions? All right, then let's thank Pavan and all our speakers this morning.